What is air? I mean, really, it's just
Yeah.
there all the time. We breathe it, live in it. But these invisible substances all around us, from the breath you literally just took, to these huge weather systems shaping the whole planet, they're all run by some pretty fascinating fundamental chemistry. Welcome to the deep dive. This is where we take your sources, could be articles, research papers, textbooks, notes, and we pull out the core insights. We give you that shortcut to really understanding a topic. Today, we're diving into the properties of gases, and we're working from a really comprehensive chemistry text, our goal,
Hmm.
to kind of unpack this invisible world surrounding us.
Exactly. And our mission really is to take these sometimes complex chemical ideas and make them clear, understandable. We'll dig into why gases act the way they do, touch on some surprising history, and show how it all connects back to, well, your everyday life. Prepare for a few aha moments, I think.
Okay, let's get into it then. Gases. They seem so different from liquids or solids. What's the fundamental thing that sets them apart? Compressibility, expansion, mixing, it all comes from one core idea, doesn't it?
It absolutely does. It's all about the space, the sheer distance between the molecules. I mean, think about the air in this room, the actual molecules. They probably only occupy about maybe 0.1% of the total volume. Seriously.
0.1%. Wow.
Yeah, the rest is just empty space. And that vast emptiness explains pretty much everything. Why gases just naturally expand to fill any container you put them in. Why they're so easy to compress, and why, regardless of what they are chemically, they always form these perfectly uniform, homogeneous mixtures, like the air we're breathing right now. Nitrogen, oxygen, totally different chemical properties, but they mix completely, perfectly.
That's a fantastic visual. So it's the emptiness that's the key characteristic then. Even if they're chemically different physically, all that space makes them act, well, almost identically in some ways, like invisible twins.
That's a great analogy, invisible twins. And yeah, when you look at what substances are gases at normal temperatures and pressures, you see a pattern. You've got the noble gases, helium, neon, just single atoms, then common diatomic molecules, things like hydrogen, nitrogen, oxygen, H2, N2, O2, and also simple molecular compounds like CO2, carbon dioxide, or methane, CH4. Generally, they have pretty low molar masses. They're light molecules, and they're usually made of non-metallic elements.
Okay, that makes sense. What about the term vapor? I sometimes hear water vapor. Is that just another word for gas, or is there a subtle difference?
Good question. It's a common point of confusion. Vapors aren't fundamentally different things. It's just what we call the gaseous state of a substance that under normal conditions we'd usually find as a liquid or a solid. So water vapor is gaseous H2O. It's just that we normally see H2 as liquid water or solid ice. A vapor is basically a gas that's close to its condensation point at everyday temperatures.
Right, okay. So that invisible air, the stuff that feels like nothing, it actually pushes on us hard. This idea of pressure, how does that actually happen on a molecular level?
Yeah, it feels weightless, but it's far from it. Pressure fundamentally comes from the gas molecules constantly moving chaotically and slamming into the walls of whatever container they're in, or slamming into us. Every single tiny collision exerts a little force. Add up billions upon billions of those collisions over a certain area, and that's pressure, force per unit area.
And the scale of this is just mind-boggling. You mentioned in the source material this idea of an air column.
Oh yeah, imagine a column of air, just 1 square meter at the base, stretching all the way from sea level right up to the edge of space. That column of air weighs about 10,000 kilograms.
10,000 kilograms, just for a 1 meter square.
Roughly, yeah. And that massive weight pressing down is what creates atmospheric pressure. At sea level, it works out to about 100 kilopascals, 100 kPa, or 1 atmosphere.
Incredible. And that pressure differential is what drives weather, right? From breezes to, well, tornadoes.
Exactly. Huge pressure differences between air masses create wind, storms, the whole lot. And historically, this wasn't always obvious. It took Evangelista Torricelli back in the 17th century to really prove the atmosphere had weight. He invented the barometer. Famously, he used a tube of mercury, inverted it in a dish of mercury, and showed that the atmosphere's pressure could hold up a column of that mercury about 760 millimeters high.
Ah, so that's where 760 millimeters of mercury comes from. And the unit torr, named after the...
Precisely. 760 torr is defined as 1 standard atmosphere. So yeah, units like atmospheres, torr, millimeters of mercury, they all stem from understanding this atmospheric weight.
Okay, beyond the weather forecast or barometers, where else does this concept of pressure show up in a really practical, maybe even personal way?
Well, a very direct one is measuring blood pressure. Right. When you get a reading, say 120 over 80, those numbers are actually in units of torr, or millimeters of mercury, which is the same thing. The cuff they use inflates to temporarily stop blood flow in your arm. Then, as they slowly release the pressure, the systolic pressure, the top number, is the pressure when the blood just starts to pulse through again. The diastolic, the bottom number, is when the blood flow is basically unrestricted.
I never realized those numbers were torr. That's a vital information for health, obviously. High blood pressure, hypertension,
Right.
it puts a huge strain on your heart because the pressure is too high.
Exactly. It means the heart has to work much harder to pump blood against that higher resistance.
Okay, so gases exert pressure. But their behavior isn't totally random, is it? There are predictable laws. I love the story in the text about the Montgolfier brothers.
Ah, yes. The first hot air balloon flight in 1783, with the sheep, the duck, and the rooster as passengers.
Incredible. They were basically demonstrating these gas laws without maybe even fully codifying them yet, showing the relationships between temperature, pressure, volume.
And the amount of gas, yeah. They heated the air inside the balloon, making it less dense than the surrounding air, which generated lift. That flight was a fantastic, if maybe slightly weird, demonstration of these core principles. Let's break them down. First up, you have Boyle's law. Robert Boyle, really a pioneer of careful experimental science. He found this inverse relationship. If you keep the temperature and the amount of gas the same, and you decrease the pressure on a gas, its volume increases, and vice versa. Increased pressure, volume decreases.
Like a weather balloon. As it goes up, the outside pressure drops, so the balloon expands. Massively sometimes.
Exactly. P and V are inversely proportional. PV calculates constant if T and N are fixed.
And apparently we use Boyle's law every time we breathe. How does that work?
It's quite elegant, actually.
Yeah.
When your diaphragm contracts and your rib cage expands, the volume inside your lungs increases.
Yeah.
According to Boyle's law, if the volume goes up, the pressure inside must go down, right? So the pressure inside your lungs becomes slightly lower than the atmospheric pressure outside.
And air just rushes in to equalize the pressure.
Precisely. Then you relax, volume decreases, pressure increases, and air flows out. Simple mechanics governed by Boyle's law.
Wow. Okay, what's next? Charles's law.
Yep, Charles's law, named after Jacques Charles. He looked at the relationship between volume and temperature, keeping pressure, and the amount of gas constant. He discovered that the volume of a gas is directly proportional to its absolute temperature. And the key word there is absolute.
Meaning temperature in Kelvin, not Celsius or Fahrenheit.
Exactly. Temperature has to be in Kelvin, because the Kelvin scale starts at absolute zero, which is theoretically the point of zero volume. Charles actually extrapolated his data and figured out this theoretical zero point must be around negative 273.15 degrees Celsius, which is now the basis of the Kelvin scale, 0 Kelvin.
So V is proportional to T in Kelvin. That's why a balloon shrinks if you put it in the freezer and puffs back up when you warm it.
That's the perfect example. VT is constant if P and N are fixed.
Okay, Boyle is PV, Charles is VT. What about the amount of gas?
That brings us to Avogadro's law. This builds on earlier work, particularly by Gay-Lussac, who studied how gases combine in chemical reactions. Amedeo Avogadro proposed something quite radical for his time, that equal volumes of different gases, if they're at the same temperature and pressure, actually contain the same number of molecules.
Regardless of what the gas is, helium versus oxygen versus CO2.
Correct. Doesn't matter. Same volume, same T, same P means same number of molecules or moles. So Avogadro's law states that the volume of a gas at constant temperature and pressure is directly proportional to the number of moles of the gas. More gas means more volume. V is proportional to N.
That's incredibly useful. It gives us a standard benchmark, doesn't it? Like the standard molar volume.
Exactly. At what we call standard temperature and pressure, or STP, which is defined as 0 degrees Celsius, that's 273.15 K, and 101.325 kilopascals, or 1 NEM. 1 mole of any ideal gas occupies a volume of 22.41 liters. It's a really handy conversion factor.
So Boyle, Charles, Avogadro, they all describe one piece of the puzzle. Is there a way to put them all together?
There is, and it's one of the most powerful equations in introductory chemistry. The ideal gas equation. It combines all three laws into a single relationship. PV equals nRT.
PV equals nRT, okay. Pressure times volume equals moles times R times temperature. And this describes an ideal gas. What makes it ideal?
An ideal gas is a hypothetical concept. It assumes two main things that aren't quite true for real gases, but are often close enough. One, it assumes the gas molecules themselves have zero volume. They're just points in space.
Yeah.
Two, it assumes there are absolutely no attractive or repulsive forces between the molecules. They just bounce around independently.
Okay, so it's a simplification. But you're saying it works pretty well most of the time. Under normal conditions.
Remarkably well, yes. For many gases at reasonable temperatures and pressures, the deviations are small.
And the R in the equation, what's that?
R is the ideal gas constant. It's basically a proportionality constant that links all the units together. Its numerical value depends on the units you choose for pressure and volume. For instance, if pressure is in kilopascals and volume is in liters, R is 8.314 cupel-molo. If you use atmospheres for pressure, R has a different value.
But temperature always has to be in Kelvin.
Always. Non-negotiable.
Oh.
Because the relationship depends on absolute temperature, starting from 0. Using Celsius would completely mess up the proportionality.
Right, so PV-nRT lets you calculate any one of those variables if you know the other three. That seems incredibly useful.
It is. You can predict how pressure changes if you heat a fixed amount of gas in a rigid container, or how volume changes if you add more gas at constant TMP.
You mentioned a really critical real-world application earlier, airbags. How does PV-nRT play into that?
Yeah, airbags are a fantastic example. They work using a rapid chemical reaction, often involving a compound called sodium azide, NN3. When triggered by a crash sensor, the sodium azide decomposes extremely quickly to produce a large volume of nitrogen gas, N2. Engineers need to calculate the exact mass of sodium azide required to produce precisely the right number of moles, N, of nitrogen gas. To inflate the airbag to the correct volume V, and pressure P within milliseconds, considering the temperature T generated by the reaction.
Wow, so they use PV-nRT to work backwards from the needed volume and pressure to figure out the N, the moles of N2 needed, and then calculate the grams of sodium azide.
Exactly. Too little gas, the airbag is useless. Too much gas, and the inflation itself could be dangerous. It has to be incredibly precise, and the ideal gas law is central to that calculation.
That's a life-saving calculation.
Yeah.
What about something like gas density? Can we use the equation for that too?
Yep. Density is mass divided by volume. We can rearrange PV-nRT and substitute molar mass for N moles. You end up with an equation for density, D in a PMRT, where M is the molar mass of the gas.
So density depends on pressure, molar mass, and temperature.
Right. Which explains why, for example, carbon dioxide, CO2, with a molar mass of about 44 kilomole, is denser than air. Average molar mass around 29 kilomole at the same T and P. That's why CO2 from fire extinguishers sinks and blankets a fire, displacing the oxygen. And it's why hot air balloons work. Heating the air, increasing T, makes it less dense, lower D, than the cooler air outside, providing lift.
Okay, that makes sense. Now, so far, we've mostly talked about single pure gases. But like air, most gases we encounter are mixtures. How do we handle that?
That's where Dalton's law of partial pressures comes in. John Dalton figured out that for a mixture of gases that don't react with each other, the total pressure exerted by the mixture is simply the sum of the pressures that each individual gas would exert if it were present alone in the same container.
So each gas acts independently. Its pressure contribution, its partial pressure, isn't affected by the other gases being there.
Exactly. The total pressure, P total, is just P1 plus P2 plus P3 and so on for each gas in the mixture. They all just contribute their share based on how much of each gas is present.
Like the example from the text Laughing Gas in Dentistry. Nitrous oxide, N2O. They don't give you pure N2O, do they?
No, absolutely not. That would be dangerous. You need oxygen. Nitrous oxide is typically administered as a mixture, often around a 2.1 ratio of N2O to O2. Controlling the partial pressures, or the relative amounts, of each gas is crucial. You need enough N2O for the anesthetic effect, but also enough O2 for the patient to breathe properly. Dalton's law helps manage that mixture precisely.
And N2O has other uses too, right? Rocket fuel and whipped cream?
Yeah, it's quite versatile. It
Yeah.
can be used as an oxidizer to boost rocket engine performance.
Yeah.
And it's used as the propellant in canned whipped cream because it dissolves really well in the fatty cream under pressure and then expands to create the foam when released.
Huh. Okay. So how do we relate the partial pressure of one gas to the overall mixture?
We use something called the mole fraction.
Hmm.
The mole fraction of a gas in a mixture, usually written as X, is just the number of moles of that specific gas divided by the total number of moles of all gases in the mixture. And Dalton found that the partial pressure of a gas, P1, is equal to its mole fraction, X1, multiplied by the total pressure, P total. So P1 equals X1 P total.
Ah, okay. So if air is roughly 78% nitrogen molecules, its mole fraction is 0.78.
Pretty much, yes.
Then the partial pressure of nitrogen in the air is just 0.78 times the total atmospheric pressure.
Exactly. It directly tells you how much of the total pressure is due to that specific gas. It's a really elegant relationship.
Okay, these laws, Boyle's, Charles's, Avogadro's, Dalton's, the ideal gas law, they tell us how gases behave, but they don't really explain why on a fundamental level, do they? That's where the kinetic-molecular theory comes in.
Precisely. The gas laws are empirical based on observation and experiment. The kinetic-molecular theory of gases provides the underlying theoretical explanation for why those laws hold true. It connects the macroscopic behavior we observe, PVT, to the microscopic world of molecules.
And this idea isn't new, is it? People have suspected atoms were moving for ages.
Oh, absolutely. Lucretius, the Roman philosopher, wrote about dust motes dancing in sunbeams, speculating about unseen moving particles. Much later, Robert Brown observed the random jiggling motion of pollen grains in water, Brownian motion.
Which Einstein later explained mathematically as evidence of water molecules constantly bombarding the pollen grains.
Exactly. But it was really Rudolf Clausius in the mid-19th century who pulled it all together into a coherent theory for gases. The theory rests on about 5 key postulates, or assumptions, about gas molecules.
Okay, what are they?
First, gases are made up of a large number of molecules that are in continuous, completely random motion, straight lines until they collide. Second, the actual volume occupied by the gas molecules themselves is essentially negligible compared to the total volume of the container. Remember that 0.1% figure, mostly empty space. Third, attractive and repulsive forces between gas molecules are also negligible. They don't really interact except during collisions. This is a key ideal assumption.
Right, like tiny billiard balls just bouncing off each other?
Sorta, yeah.
Ah.
Fourth, when molecules collide with each other, or the walls, energy can be transferred, but the average kinetic energy of all the molecules remains constant as long as the temperature doesn't change. Collisions are perfectly elastic on average. And fifth, this is the crucial link, the average kinetic energy of the gas molecules is directly proportional to the absolute temperature in Kelvin.
So temperature isn't just some abstract scale, it's literally a measure of the average motion energy of the molecules.
Exactly. Hotter gas means, on average, molecules are moving faster, hitting the walls harder and more often. Colder gas, slower molecules.
And at the same temperature, molecules of any gas have the same average kinetic energy.
Correct. A helium atom and a big xenon atom at the same temperature have the same average kinetic energy. But since kinetic energy depends on mass and speed, Ke equals 12 millivitafars, the lighter helium atom must be moving much, much faster on average to have the same energy as the heavier xenon atom.
Ah, okay, that makes sense. So this theory explains the gas laws. How does it explain Boyle's law, for instance?
Well, think about it. Boyle's law says if you increase the volume at constant T and N, the pressure decreases. Why? According to the theory, if the volume is bigger, the molecules have to travel further, on average, between collisions with the walls. So even though they're moving at the same average speed, because T is constant, they hit the walls less frequently per unit area. Fewer collisions per second means lower pressure. It explains Boyle's law perfectly.
In Charles's law, increased T at constant P.
Increased T means molecules move faster, hit the walls harder, and more often. To keep the pressure constant, meaning the force per unit area stays the same, the volume must expand, giving the molecules more room, reducing the collision frequency just enough to compensate for the harder impacts. Volume increases with temperature.
It all fits together beautifully.
Yeah.
Okay, you mentioned lighter molecules move faster at the same temperature. How much faster?
We can quantify that. The typical speed we talk about is the root mean square, or arms speed. It's kind of a specific type of average speed. And this arm speed is inversely proportional to the square root of the molar mass.
Yeah.
So speed goes like 1 m.
Meaning if one gas is 4 times heavier than another, it moves half as fast.
On average, yes. That square root relationship is key. Lighter gases are significantly zippier.
And this difference in speed has real consequences, right? Like effusion. What's effusion again?
Effusion is the process where gas molecules escape from a container through a tiny, tiny pinhole into a vacuum or region of much lower pressure. Thomas Graham studied this and found Graham's law of effusion. The rate at which a gas effuses is inversely proportional to the square root of its molar mass, rate 1 ear.
Which perfectly matches the speed relationship.
Exactly. Faster molecules hit the vicinity of the pinhole more often, so they have more chances to escape.
That's why a helium balloon, molar mass 4 gmol, deflates way faster than an identical balloon filled with air, average 29 gmol, or nitrogen, 28 gmol. The helium just zips out much quicker.
Precisely. And it's also why they add that smelly compound, ethanethiol, to natural gas, which is mostly methane odorless. Ethanethiol is relatively light, so its molecules effuse and diffuse quickly, allowing you to smell a leak fast.
Okay, so effusion is escaping through a hole, but you just mentioned diffusion. That's different, right? Like perfume spreading across a room.
It is different, and actually more complex in practice. Diffusion is the gradual mixing of molecules of one gas with molecules of another, driven by that random molecular motion.
But wait, if gas molecules are moving at hundreds of meters per second, like you said earlier, why does it take time for a smell to diffuse across a room? Shouldn't it be almost instantaneous?
Ah, great question. It seems counterintuitive. The molecules are moving incredibly fast, but they don't travel in straight lines for very long, especially at atmospheric pressure. They're constantly colliding with other molecules billions of times per second, about 10 billion collisions per second for a typical air molecule.
10 billion.
Yeah. So each collision sends the molecule off in a new random direction. The path is incredibly zigzaggy. The average distance a molecule travels between these collisions is called the mean free path. And at atmospheric pressure, it's actually very short, maybe tens of nanometers.
So even though the instantaneous speed is high, the actual net distance traveled in one direction over time is much, much slower because of all the collisions. It's like a chaotic random walk.
Exactly. That's why diffusion, the overall spreading out, is significantly slower than the molecular speeds themselves would suggest. But the principle that lighter molecules diffuse faster still holds. And this very principle had a huge historical consequence during World War II.
The uranium enrichment.
Yes. Natural uranium is mostly uranium-238, but the isotope needed for the first atomic bombs was the slightly lighter uranium-235. Separating them is incredibly difficult because they're chemically identical. The solution was to convert the uranium into a gas, uranium hexafluoride, UF6. Then they forced this gas to diffuse through thousands of porous barriers. The UF6 molecules containing the lighter U-235 isotope are just slightly faster than those with U-238, so they diffuse through the barriers a tiny bit quicker.
And by repeating this thousands of times, they could gradually enrich the concentration of U-235 based on that tiny difference in diffusion rate.
An incredible feat of engineering, based directly on Graham's law and the kinetic-molecular theory.
Wow. Okay, throughout this, we've often relied on the ideal gas model. But we know gases aren't truly ideal. When does that model start to break down? When do real gases stop behaving ideally?
The ideal gas assumptions work best at low pressures and relatively high temperatures. They start to fail significantly under two main conditions. One, at very high pressures, say above 10 atmospheres, about 1 MPa or 1,000 kPa or so. Two, at very low temperatures, especially those getting close to the point where the gas would normally condense into a liquid.
Okay, why do those conditions cause problems for the ideal model?
It comes back to the two main simplifying assumptions we made. First, the assumption that molecules have negligible volume. At low pressures, the molecules are far apart, and their own size is tiny compared to the total volume. But if you squeeze the gas down to a very high pressure, the molecules get much closer together. Suddenly, the volume the molecules themselves occupy becomes a significant fraction of the container's volume. There's less empty space for them to move in than the ideal V assumes. This tends to make the measured volume slightly larger than predicted by PV and RT at very high P.
Okay, so molecular volume matters at high pressure. What's the second reason?
The second assumption was that there are no intermolecular forces, no attraction or repulsion between molecules. Again, at low pressures and high temperatures, molecules are far apart and moving fast, so any weak attractions don't have much effect. But at low temperatures, molecules are moving slower. And at high pressures, they're closer together. Under these conditions, the weak attractive forces, like van der Waals forces, do become significant. They pull molecules slightly towards each other. Think about a molecule about to hit the container wall. It gets tugged back slightly by its neighbors. This reduces the force of its impact on the wall.
Ah, so the actual real pressure exerted by the gas is lower than the ideal gas equation would predict because of these attractions.
Exactly, especially noticeable at lower temperatures where molecules aren't energetic enough to easily overcome the attractions.
So for someone like an engineer designing, say, a high-pressure natural gas pipeline that might operate across wide temperature ranges, they can't just use PV and RT and call it a day.
Definitely not. The deviations would be too large for accurate engineering. They need equations that account for these real gas effects. The most famous one is the van der Waals equation. It basically modifies the ideal gas law. It adjusts the measured pressure upwards to account for the attractions lowering the real pressure using a constant A, which is specific to each gas and represents the strength of its intermolecular forces. And it adjusts the container volume downwards, subtracting a term NB, where B represents the volume occupied by the molecules themselves, to get a more realistic free volume for the molecules to move in.
So it adds correction factors, A for attraction and B for molecular volume, unique to each gas.
Precisely. P plus ANV times VNV equals nRT. It's more complex, but much more accurate for real gases, especially under non-ideal conditions. Those A and B values are tabulated for different gases and are essential for real-world calculations in industry.
What an incredible journey. We started with just asking, what is air? And we've ended up seeing how these invisible particles, their motion, their collisions, their tiny attractions, govern everything from breathing to weather to airbags to industrial pipelines, even nuclear technology.
It really shows how fundamental these principles are. The gas laws, the kinetic theory, the deviations for real gases. They provide this powerful framework for understanding a huge range of phenomena.
It's truly clear that this seemingly simple state of matter, gas, is actually incredibly complex and dynamic when you look closely, all driven by these invisible forces and the constant dance of molecules.
Absolutely. And maybe the thought to leave you with is this. If we can uncover such elegant laws and intricate relationships governing something as seemingly simple as gases, just by observing carefully and thinking critically, what other hidden orders, what other surprising connections might be waiting to be discovered in the world all around us if we just learn how to look closely enough and ask the right kinds of questions.
That's a really powerful thought. Something definitely worth mulling over. Thank you for joining us on this deep dive today.